Okay, we are live.
Brilliant. Hello, everyone. Welcome to the second press briefing of the day at 4:30 p.m. Eastern Standard Time for January 14th, 2021 at the 237th meeting of the American Astronomical Society. My name is Tarini Konchadi. I'm the AAS Media Fellow, and I will be your MC for this briefing. I'm assisted by AAS Press Officer Rick Feinberg, AAS Nova Editor Susanna Kohler, and Astrobytes media intern and graduate student at West Virginia University, Haley Wall. Today, Haley will be handling the Q&A, and Susanna will be keeping an eye on the press conferences Slack. And Rick will handle about anything else that should come up. There are at least 3 releases that will be going out with this briefing. And the materials associated with yesterday's briefings should be uploaded on the AAS website under Astronomy in the News, tweeted from AAS_press, and they should also be on the online press kit. We are recording this briefing as well as streaming it to YouTube. If you haven't been to one of these before, the way it works is I give a brief introduction to the topic of the briefing and introduce our panelists. The panelists will then speak in order, and at the very end, we will have our Q&A. If you would like to ask any of our panelists a question, please use the Q&A box at the bottom of your screen. And when you do ask a question, be sure to include your name, affiliation, and who that question is for. If you see that someone's asked a question that you also have, you can upvote that question and raise it in the queue. Our panelists won't be answering the questions via text, just so we can keep everyone abreast of what's happening in the Q&A, especially those on YouTube. We'll only answer those questions live during the Q&A session after our panelists have spoken. For anything that's not Q&A, you can use the Slack channel for press conferences. It begins with 3 zeros. The topic of this briefing is Evolving Stars and Nebulae 1, because just like with galaxies and quasars, we had a lot of really fascinating abstracts submitted on that topic. In order, our speakers are James Davenport from the University of Washington, with the rise and fall of a remarkable eclipsing binary star. Next, we have Ethan Kruse from NASA's Goddard Space Flight Center, with hundreds of thousands of eclipsing binaries discovered through machine learning. Third, we have Sagiv Shiber from Louisiana State University, with Unbinding the Stellar Envelope in Grazing envelope evolution. Next, we'll have Daniel Patnaude from the Center for Astrophysics, Harvard and Smithsonian, with exploring the supernova remnant connection. And rounding us off, we have John Banovetz and Danny Milisavljevic with the Center of Expansion and Age of an oxygen-rich supernova remnant. And with that, I will turn it over to James.
Excellent. All right, I'll start sharing my screen here. Okay, hopefully everybody can see that.
Yes,
We can.
Excellent, thank you. All right, I'm going to spend a couple minutes getting us started talking about one remarkable system, the rise and fall of an eclipsing binary that's known as HS Hydra, and that's it in the middle there, right between the letters HS Hydra. Bright little star there. This is work that I'm doing, of course, with a team of students at a bunch of different institutions and with support of a lot of different agencies. And so I want to just start by just thanking everybody who's participated and who's been working so diligently during this difficult time remotely. HS Hydra is an eclipsing binary star. Come on, slides, there we go. It's an eclipsing binary star. Now, we've had lots of eclipsing objects or transiting objects this week, so this is probably a primer at this point that's totally unnecessary, but an eclipsing binary star is 2 stars that happen to have that special alignment where one star passes in front of the other from our line of sight, and so you get this characteristic big dip in the middle when the smaller star passes in front of the bigger star, and smaller dips when the arrangement is flipped. This is the classical picture of an eclipsing binary star, and they've been known for centuries. They're a really classical topic in astrophysics. And HS Hydra has been known to be an eclipsing binary star since at least the 1960s. What makes HS Hydra a remarkable star is that its eclipses are disappearing. This is a rare type of eclipsing binary that we think the orientation is actually shifting. The discovery plot here from Zasha and Pashka, which we've recreated here on the left, shows these deep eclipses in the 1970s, very easy to detect, obviously an eclipsing binary. And they went back and found this archival data from the 90s and the early 2000s, and you can see this, it's a little bit noisy, but you can see the amplitude is shrinking with each subsequent visit for this system. And they were able to infer from this data that there must be some third star in the system on some wider orbit that's not eclipsing, probably much smaller, but it's causing this whole system to sort of tumble through the sky as it eclipses. And from our line of sight, it causes the inclination, we would say, that special angle that allows them to line up and show us these eclipses. That inclination is evolving. A little more simply diagrammed, which I like. In the 1970s, when it was discovered, the secondary star in purple passed almost exactly right over the middle of the primary star. By the early 90s, the inclination had shifted. By the mid 2000s, the inclinations were really, really steep. And Zasha and Pashka made a prediction that in 2022, somewhere around 2022, this critical inclination would occur where the system was no longer eclipsing. There's a bit of uncertainty on this because the data were a little noisy, and this is what caught our eye. And so today I'm going to introduce you to some new and some old data for HS Hydra that's gone unanalyzed. Our new data comes from a really lucky observation from TESS, the Transiting Exoplanet Survey Satellite. This is just the sky map of where it's looked now, completing its 2-year, 80% of the sky coverage. And TESS really got a remarkable look at HS Hydra. Here is the light curve, the sort of phase-folded or orbital period-folded light curve of HS Hydra. And there are these tiny little eclipses, these little dashes in the data, underneath this sort of smooth modulation, tiny eclipses in this 25-day chunk of data. It's a really cool set of data. These look, honestly, they look like exoplanet transits more than eclipsing binary eclipses. For sort of scale, here is, I've used PowerPoint to just shrink this down onto roughly the same scale as that original discovery light curve, maybe even should be smaller. And you can see the eclipses are teeny tiny, barely visible compared to these giant deep eclipses that it was discovered with. And the eclipses happen a little bit later in the orbital phase, about 5 hours later. These are both indications that there's this third star causing the whole system to sort of tumble. So a lucky view from TESS, indeed. We caught it right as it was grazing, right near that critical inclination value where it would no longer be an eclipsing binary. And that's pretty cool. Now some old data, some new old data, as it were. And that comes from a digitized photographic plate archive out of Harvard called the DASH Project. This is a century's worth of old photographic plates that have been uniformly mapped and digitized and cataloged, and all of the log books as well. So here's the sort of two pieces of information you need. You need the plate on the right, the image, and you need the metadata, the data and the metadata, to put it onto a system of data that we can use seamlessly with this new data from TESS. And what does the data look like here? Well, here is the same sort of phase folded diagram. You can see on the top, there's no apparent eclipses. This is basically just noise, but the data reaches back all the way to 1893, which is really remarkable to me, a 125-year baseline from the TESS data. Then somewhere around the 1920s, 1930s, the eclipses start to become visible sort of in this blue band. And then by the sort of post-war, middle of the century, the eclipses, as expected, are very strong. There's really remarkable eclipsing going on here. And this leads us, the combination of this old archival data mixed with the brand new data from TESS gives us this rise and the fall of HS Hydra, that there was this rise in the sort of eclipse depth, how deep that eclipse was. It gets bigger and bigger, or deeper and deeper in the DASH data through the photographic plate area. This is really the beginning of modern survey astronomy, where we're keeping these very detailed records of how the sky is changing. Then in about 1959, it reaches its maximum, or the eclipse is straight on the equator of the primary star. And we enter the space race, the space era, the digital sky, the digital instrument era, where we start to have photoelectric measurements. And as our technology improves, the system's signal gets smaller and smaller, all the way to the point where today we have this remarkable platform in TESS that's flying in outer space and capturing really amazing data for HS Hydra. And that caught it just in its waning days as an eclipsing binary. And similarly, if we transform this into the implied inclination, we think that somewhere around February, so probably 3 or 4 weeks from now, we will reach that critical inclination here. The test data suggests that critical inclination is happening really soon, but that the eclipse depth is probably so small that even TESS with this remarkable precision can't measure it anymore. So we think that HS Hydra is now a former eclipsing binary. That is, until the future, where I'll see you at AAS 585, something about 200 years from now, where we think the system will continue to tumble, and we think the eclipses may start again. Now, there's, of course, some uncertainty, so it might be a couple years before that. But HS Hydra, we believe, will become an eclipsing binary again someday. And until then, we'll keep using TESS to study these systems, these rare eclipsing binaries. Only a few dozen of these evolving systems are known, so they're really special. And this is, I think, a remarkable platform to do this work. All right, and then I think I'm supposed to hand it off next to Ethan.
Excellent. Thank you, Dr. Davenport. Here we go. All right. So I'm going to be talking today. James just gave a great introduction here to what eclipsing binaries are and the power of what you can do with even one of them. I'm going to be talking today about what you can do with what happens if you have 100,000 eclipsing binaries. And how we have used machine learning tools to discover them. So I really don't even need to give this slide anymore because we just saw it. Eclipsing binaries are in fact when two stars orbit each other and cause these dips in light. And those dips that you can use to measure exactly how large these two stars are. And if you have other observations like radial velocity, you can measure the masses of these stars and get really, really precise masses and radii. And in fact, eclipsing binaries really are the best way to get really precise masses and radii of stars. And with that, we can use that to test all our theories about how the universe works, how stars form and evolve, and test and see if we are getting things right. And our models can predict stars of the right mass and radius and things like that. And you really need lots and lots of these to do this and cover all different types of stars in all environments. And if you have lots of these as well, of course, you're going to come upon some weird cases, just like HS Hydra, where you get individual case studies of stars that are doing completely unusual things like disappearing their eclipses. Now, to find an eclipsing binary star, you need to sit there and stare at the star for a while, or get lucky and just happen to catch an eclipse happening. But the best way to do this is to go to space. And the Kepler telescope, which of course is famous for discovering planets, is also great at discovering eclipsing binaries, where you're just staring at the same stars in this patch of sky up here, and just watching those stars and looking for those dips in brightness that signal either a planet or an eclipsing binary. However, the drawback of Kepler was that it only looked at this tiny little patch of sky up here, whereas we now have TESS, which, as we just saw, completely revolutionizes things. We go from that little patch of sky to 75% of the sky. And now with TESS, we can look at all of these millions and millions of stars and start to observe them, figure out how many of them are eclipsing and what's going on with them. So that is the goal of our project here. And just to put the numbers in comparison of how much we're expanding things compared to what Kepler did as the sort of previous state of the art. Kepler looked at 200,000 stars. Our work here is looking at 60 million. Kepler, its job was to only look at basically sun-like stars. Whereas with TESS, of course, it's looking at the entire sky. We can discover stars of all types. And like I just said, Kepler only studied a tiny fraction of the sky. TESS is covering 75% of the sky. And so with all of that combined, we're able to go from Kepler's 3,000 eclipsing binaries, which was already a wonder, to what we now think are right around 300,000. So 2 orders of magnitude more eclipsing binaries to work with, to study, and to use. But to do all that, we have to go from raw test data here up to what the light curves. And to create 60 million light curves is quite a feat. And so we made use of the Discover supercomputer at NASA Goddard. I've been told that we've used somewhere around 100 CPU years of time just generating these light curves. So we now have the light curves of 60 million stars on our machines at NASA Goddard. From that, we can then start to ask, of those 60 million, how many of them are showing dips like this that indicate eclipsing binaries? However, 60 million is a lot bigger than the 200,000 from Kepler. And it is just an overwhelming number for the traditional tools that we used to have. And so we're turning instead to new tools that are much faster. And so we've created a neural network that is specifically designed to scan light curves for eclipsing binaries. And it can do this in fractions of a millisecond. So each star, it can examine and calculate in just a tiny fraction of a second. Yes or no, does this star have a sign here? Like, so these arrows are pointing at pieces of the light curve that the neural network has triggered on or activated on and says, I think I found an eclipse. And that's what we're looking for. As we feed in all 60 million stars to this neural network, it can quickly scan through them and spit back out a result that tells us yes or no, do we see an eclipse here, without having to go through all the traditional search tools that we've done before. And so this has revolutionized our work here, and this neural network has allowed us to find all these. And so I just want to really briefly show the results. So at first, I'm just going to show our small test run, which was in sectors 14 and 15 from TESS, where we found 20,000 eclipsing binaries. And I'm comparing the period distribution here of our eclipsing binaries to those from Kepler. So Kepler is in orange, our results are in blue. And you can see that the distributions very much look the same. So our neural network is working. It's finding the same types of eclipsing binaries as Kepler was, but all over the sky. However, if we switch from relative counts to raw numbers, ours again are in blue and Kepler is in orange. And you can just see that we're just dwarfing what Kepler was doing. And this was in our 20,000 EB small test run as we're making sure all the kinks are worked out. And so moving forward, I'm just going to end here on this final slide that we have all 26 sectors of the original TESS mission in hand. We have fed them through the neural network. It has returned 458,000 signals it thinks have EBs in them. Of those, about 300,000 are probably real. I don't have time to talk about how we've sort of filtered out false positives, but our final catalog is going to be somewhere on the order of 300,000 eclipsing binaries here. And just Kepler, the Kepler catalog, which was previously the state of the art, gets reduced to basically a single orange pixel down here at the bottom of this plot, where we're showing the total numbers as a function of period in our catalogs. So I'm just really excited to see all the different signs you can do, as you now have 300,000 different eclipsing binary systems to look at and figure out, find all the cool ones and figure out the sort of bulk statistical studies you can do with this. Thank you. And with that, I think I'm passing on to Sagiv.
Thank you, Ethan. I will share my screen. Okay. Hello, everyone. My name is Sagiv Shiber. I'm currently a postdoc at Louisiana State University. I will discuss the unbinding of the envelope in Grazing envelope evolution. I will show results from recent three-dimensional simulations I conducted together with Roberto Iaconi from Kyoto University. Grazing envelope evolution is an evolutionary stage in stellar binary systems. The starting point is a binary system in which, due to unstable mass transfer, the orbital separation shrinks. Specifically, we look at unstable mass transfer that is caused by an evolved star, which overflows its Roche lobe. The mass transferred from the primary envelope is accumulated around the companion and forms an accretion disk. Now, the key ingredient in the Grazing envelope evolution is that the accretion disk accretes the envelope mass at a high rate such that it launches jets. You can see a sketch of this process in the figure here, taken from one of the simulations. The jets are launched in perpendicular to the orbital plane, and they remove mass from above and below the companion, preventing its complete engulfment. If jets are not able to form, or if they are inefficient in removing mass, the companion will exhibit gravitational drag forces, which will pull it deeper into the envelope. Efficient jets, on the other hand, could diminish the gravitational drag forces, and the companion will stop spiraling in. In previous study, we performed three-dimensional simulations that include jets that are launched from the companion and self-consistent gravity for a particular system. In the current study, we expanded the analysis by investigating the effect of different companion masses while keeping all the other parameters constant. Here I show a three-dimensional visualization of the Grazing envelope evolution. The white circle is a 0.1 solar mass main sequence star, and at the center there is the primary star, a red giant branch star which has a mass of 0.9 solar mass. The companion will start slowly spiraling in towards the primary envelope while constantly launching jets. We will see the jets coming out from the companion in blue. In the beginning, the interaction is mainly due to tidal forces, and a bulge is formed in the primary envelope. At some point, the bulge emerges from the primary surface and starts trailing the companion's movement. Gravitational drag forces act to shrink the orbit, and the companion starts spiraling into the envelope. When the companion encounters the envelope, the jets unbind the envelope layers with which they interact. More and more envelope mass is removed as the companion spirals in deeper into the inner, more dense envelope. The unbound parts of the envelope are flowing in all directions with a growing outflow rate. As the orbit stabilizes, the jets have no more gas to interact with, and the outflow weakens. The result is a closed orbit, which is somewhat eccentric. So how much do the jets unbind? For the 0.1 solar mass companion, 65% of the envelope will become unbound by the end of the simulation. For higher companion masses, a smaller fraction of the envelope is unbound. This is in part because we kept the same jet's power in all the simulations, while the system with heavier companions are more gravitational bound. When we simulated equivalent simulations without jets, the amount of unbound mass was about 8% at most. Here I show the final state of two simulations. On left, the simulation included jets, and on the right, they did not include jets. There is a notable difference between the outcomes of the two simulations, and the operation of the jets is clearly seen. Edge on, we see that the jets remove the envelope from below and above the companion. Face on, we see that the jets prevent the engulfment by high density gas, and also in the simulation with jets, we see that outside the companion orbit, the density steeply drops, and the radius of the primary is considerably shrink throughout the evolution. While without jets, the envelope is inflated and remains bound. This drop in density outside the companion location is throughout most of the evolution. Here I show density profiles on a straight line, starting from the primary's core, going through the companion and outside to the companion at 5 times. You can see that outside the companion location, there is a steep drop in density at all of the 5 times. This is a clear indication of a grazing orbit in which the primary radius shrinks simultaneously with the separation as the companion spirals into the envelope. The jets also affect the geometry of the outflow. In a regular common envelope evolution, the outflow is concentrated around the orbital plane. This is expected by theory and also seen in simulations. With jets, we get faster outflows towards the pole, significantly faster than the outflow towards the orbital plane. Additionally, for lower mass companion, the mass outflowing towards the poles is as massive as the mass outflowing towards the orbital plane. In these systems, jets produce a bipolar shaped outflow. These findings aligned with observation of bipolar planetary nebulae, where the rotation axis of the binary system at the center of the rotation, in the center of the bipolar nebula, was found to coincide with the axis of the nebula itself. To summarize, we investigated the Grazing envelope evolution, where a main sequence star companion accretes mass from an evolved red giant branch star and launched jets that interact with the envelope. We simulated several different companion masses, finding efficient unbinding of the envelope in lower mass companions. The simulation of the 0.1 solar mass companion is the first to demonstrate a complete Grazing envelope evolution. By reproducing theoretical models in three-dimensional simulation, we strengthen the feasibility of Grazing envelope evolution. In addition, the jets produce bipolar outflow, which later can yield a bipolar nebula. For more details, please visit my iPoster, and thank you for listening. Okay, I will now go ahead to the next speaker.
Thank you. Good afternoon, everyone. Oops, share, sorry. Oops, I'm sorry. Can you see that? Damn it. Oh, share screen. I apologize.
It's okay. We don't see the screen sharing yet.
Yeah. Share. There we go. Play from start.
That's better.
Okay. I'm Dan Patnaude, and I'm going to tell you about how we explore the supernova and supernova remnant connection by way of late time cadence X-ray and optical observations of a nearby supernova. So we currently observe hundreds, if not thousands, of supernova per year, but most of them are too far away and they fade very quickly. The reason is because the emission is from the stellar debris, which is illuminated by the radioactive byproducts of the explosion. And therefore, as the debris expands into its environment, it becomes lower and lower density. On the other hand, supernova remnants are characterized by interactions with their surroundings. But unfortunately, most of these are old, hundreds to thousands of years old, and we only have a small sample size of them. So it's really rare to be able to watch a supernova become a remnant in real time. Of course, the exception to this, there's always one exception, is 1987A, which we've been following since it was first discovered in 1987. But even that object disappeared for a few years before it reemerged. So now we have a new example of this supernova to supernova remnant evolution with this other object called supernova 1996 CR. This is an object which is located in the nearby Circinus galaxy, which is around 14 million light years away, 4.2 megaparsecs. Now, we didn't actually observe this to explode, but it was discovered serendipitously with the Chandra X-ray Observatory in 2000. And by looking at the early evolution of this object, the researchers were able to date its explosion back to late 1995 or early 1996. Now, HST images of this galaxy actually reveal a very bright point source, which is the supernova, and it's surrounded by a fainter diffuse region, which is associated with a nearby cloud of hydrogen, which we generally call an H2 region. In the X-rays, it's one of the brightest objects in the galaxy. This is a Chandra image of the Circinus galaxy and the supernova 1996 CR, and it outshines just about everything in that galaxy except the host AGN. It's one of the most luminous sources in that galaxy. The X-ray light curve has actually shown some very remarkable behavior since it was first discovered. Now, as I said, we didn't actually observe this occur in 1996, but we can go back and look at archival data, and that's what was done here. And they showed that a few years after it exploded, it still was not detected with the current generation of X-ray telescopes. But then when it was detected, it had increased in brightness by a few orders of magnitude, and it continued to evolve until it started to fade away. And the changes in this light curve that we see actually inform us a great deal about the evolution of the star prior to it exploding. Optically, it's undergone a similar revolutionary evolution. So what I'm showing here is a spectrum from 2006, roughly 10 years after it exploded, and then again in 2017, taken with the Magellan Bada telescope, excuse me. In 2006, the spectrum was actually quite unremarkable, and it was dominated by emission from that nearby hydrogen cloud, the H2 region. There was evidence for broad, fast-moving ejecta. It was seen by emission from optical lines from oxygen. But when we look 10 years later, you can now see that the spectrum is dominated by emission from that high-velocity oxygen. And you can just see how broad that oxygen is relative to the emission from the nearby cloud. We can measure that velocity, and it turns out that it's moving at around 2,300 or 2,400 kilometers per second. And this is 20% slower than the oxygen was moving in 2006. Additionally, we're starting to see emission from other heavier elements, the actual products of oxygen burning, such as sulfur and argon. And what these new observations suggest is that the emission that we're observing now is from a deeper layer of the ejecta than that which was observed previously. And furthermore, if you compare this object to young supernova remnants, such as this object I'm showing in the bottom left-hand plot, which is an object called SNR NGC 4449-1. I'm sorry, they don't all have great names. These two spectra look remarkably similar. Now, this object is a supernova remnant, and we can now say that 96CR is also evolving into the supernova remnant stage. So this gives us a direct picture of what happens to a star when it transforms from a supernova into a remnant. Now, the X-ray has actually followed a similar remarkable evolution. Early on, when it was first detected in 2000, the blast wave from the supernova shock was basically dominated by a hot thermal continuum of X-ray emission. But as it was continued to be followed over the next 10, 15 years or so, you start to see this rich forest of line emission starting to form in the spectrum. And these are things, these are lines from elements such as silicon and sulfur. So these are the products of the explosion. Our latest Chandra observation, which we took in 2018, actually shows an X-ray spectrum that is more akin to what we would observe in a supernova remnant, something like Cas-A or EO102 or other objects. It has bright emission lines from elements which are actually formed during the explosion. And you can see that where we see iron and sulfur and silicon, and then we're starting to see the emergence of other elements such as neon and magnesium. And this is all debris from the star, from when the star exploded. But as I had said earlier, that changes in that light curve of the X-ray actually inform us a great deal about the environment around massive stars, such as the parent star for supernova 1996CR. So the reason this is true is because a supernova shock basically acts like a time machine, and this allows us to reconstruct the evolution of the star before it exploded. For every year that a supernova shock expands into its environment, it's looking back in time upwards of 1,000 years of evolution of the progenitor star. So for something like 1996CR, where we've been following it for a little bit more than 20 years now, we're looking at the last 20,000 years of stellar evolution. And this is something that we very rarely can do with supernova because they're so faint and they're so far away. Excuse me. And in the case of 96CR, what we found was that brightening that we observed in the X-ray coincides with some sort of mass ejection event caused by during the progenitor's life in the last 1,000 years of its evolution. And then as we continue to follow its evolution in the X-ray, we see that eventually the blast wave has broken through this circumstellar shell, we'll call it, and now it's evolving into a more normal environment that you would expect to find around a massive star. And this is exactly what we observe when we look at older supernova remnants, such as Cas-A or EO102, which will be discussed next. So just briefly in summary, our recently obtained spectra have revealed dramatic changes in the properties of the emission in the optical. And what they tell us in particular is that we're now probing the energetics and the composition of the deeper layers of the ejecta of the star. So in 2006, we were looking sort of at layers which are closer to the surface, and as the supernova has evolved. We're looking deeper and deeper into the interior of the explosion. Supernova 1996 CR now bears a strong resemblance to young supernova remnants that we're all familiar with, such as Kruse in our own galaxy. And the X-ray evolution, it paints a picture of an object which is evolving into a remnant, and it's rich in line emission that allows us to probe the products of the explosion, the nucleosynthesis that occurred when the star exploded. And most importantly, and finally, the changes in this X-ray emission have actually allowed us to reconstruct the mass loss history of the progenitor. And we can place this remnant, or this supernova/supernova remnant, in context with other like objects like supernova and supernova remnants. So with that, I'll turn it over to John Banovetz and Dan Milisavljevic.
Just give me 1 second. All right. Hi, thanks for having me here today. My name is John Banovetz, and I'm a graduate student at Purdue University. And today I want to present on how our group was able to determine the center of expansion and age of a nearby supernova remnant using 2 Hubble Space Telescope images taken 10 years apart and with the same configuration. First, I just want to say I did not do all of this by myself. This work was made possible by a NASA grant, along with help from my advisor, Dan Milisavljevic, along with other collaborators shown here. So let's start with the motivation behind this research, and that is to understand supernovae. Supernovae are one of the most common astronomical events, with one happening every second in the universe. However, because they're so far away, we aren't able to resolve these energetic explosions, and we don't know the driving forces behind them. Luckily, their ejecta stick around, creating supernova remnants. Supernova remnants allow astronomers to have insight into supernovae that occurred thousands of years ago, and some are even close enough that we can resolve them into 3D their explosion to 3D reconstructions, as seen here with Kruse. And now, before we get too far ahead of ourselves, there's 2 fundamental properties of a supernova that we need to know. When the supernova exploded, its age, and where it exploded, its center of expansion. And these are the questions that we're trying to answer for EO102. EO102 is seen here with the different colors of red, green, and blue, indicating ejecta from its parent supernova explosion going away from us in the plane of the sky and towards us respectively. So our goal is to narrow down EO102's age and center of expansion. And we will do this by measuring the proper motion of its ejecta. And so the first step that we did is we use an image from 2003 taken by the Hubble Space Telescope, which I now have shown here in grayscale. And then we used an image taken 10 years later by Hubble using the same instrument and filter as before. Using the same instrument and filter between the 2 images allow us to measure the proper motions of individual knots of ejecta, which other studies were not able to do. And so I'm now going to blink between the 2 images. I would keep your eyes around the edge of the remnant, as the shift can be very subtle. And so we see the shift happen throughout the entire remnant. And now we're going to just zoom into a portion of the remnant to see it more clearly. So measuring the shift with individual knots of gas allows us to determine the center of expansion and age of EO102. And I'll illustrate how we do that here. So I just have a zoomed in region of the remnant that I'm going to play on loop from the previous slide. And so the first step that we need to do is figure out the center of expansion. And we do this by looking at an individual knot of gas, like this one here, and we track it between the 10 years in order to find its trajectory and speed. And so to find the center of expansion, we repeat this for many knots. and then we trace back their trajectories towards the inside of the remnant. And this will give us the center of expansion. And now that we know where the star exploded, we can determine its age. And we do that by figuring out how long it took the knot of gas to get from the center of expansion to where it is today. And so let's do that with EO102. First, trying to figure out its center of expansion. So I have EO102 pictured here. Now I'm going to overlay the 45 knots that we used in our study in white and their corresponding trajectories in red. And so you can see that, unfortunately, the trajectories don't line up as nicely as we would like. So in order to find out the center of expansion, what we did is we calculated the point that had the shortest distance between it and the other 45 trajectories. And this is our best estimate for the center of expansion. And this point is shown in yellow right here. And so now that we have the center of expansion, we can determine the age. Ideally, we would use all the proper motion measurements to do this. However, thanks to the high resolution of the Hubble Space Telescope, we found that there was an asymmetry in the proper motion measurements of the knots, possibly indicating a deceleration of some of the knots due to an inhomogeneous environment. So because of this, we opted to only use the fastest knots, as they wouldn't have slowed down as much. And they're in cyan and located here. Using these knots, we found an explosion age of 1,738 plus or minus 175 years. So now we know where and when EO102's parent supernova exploded. Knowing these values, we can learn more about EO102. One of EO102's most recent developments was the identification of a possible neutron star. This happened in 2018, where Voigt et al. Found an X-ray point source located in the crosshairs in the left figure that they said could be a possible surviving neutron star from the parent explosion. On the right, we have the candidate neutron star in purple, a previous center of expansion estimate in red, and our center of expansion estimate in yellow. Using our new center of expansion and age, we were able to determine that this candidate neutron star would have experienced a kick of 1,070 kilometers per second. If confirmed, this would be one of the highest kick velocities of a supernova remnant associated neutron star. However, the true nature of this neutron star is still unclear. So in conclusion, we were able to find a new center of expansion and age for supernova remnant EO102. This was only possible due to the high resolution, sensitivity, and longevity of the Hubble Space Telescope. And we were able to utilize 2 images taken 10 years apart using the same instrument and filter to measure the proper motions of individual knots of gas in order to do this. Now we are able to wind back the clock and discover more things about EO102, such as things about its progenitor and its explosion, and possibly the progenitor system that caused this inhomogeneous environment to occur. We go into more details about these implications in our associated paper, which was submitted to the Astrophysical Journal and is under the refereeing process, along with my poster, which the number is on the bottom bullet point. And we can use these values in future studies, such as recreating EO102 in 3D, which is showcased by Dan's poster, and which the number is given here. Thank you.
Thanks, everyone. I see there are a lot of questions. So Haley, I will hand things off to you.
Thanks. So the first one comes from Leslie Sage from Nature for James. What's the mass of the third star and what's the limit on its luminosity?
We don't have a precise mass because this data doesn't constrain it, but the best guess is the mass is probably a M dwarf, so probably about 10% the mass of the sun, and its luminosity is probably about 5 to 10% that of the sun. So it's a pretty small little star in the outer orbit.
Great, thanks. The next one comes from Jan Hatterbach, freelance, for James. What causes the, I'm guessing that's sinusoidal-like motions of the flux in the test data? Just a sinus-like modulation.
Yeah, that sort of smooth sine wave. The two stars, which are both a little bit more massive than the sun, the two stars are close enough that they're gravitationally extending each other. They're pulling on each other with tidal forces, just like the moon pulls on the ocean on the Earth. And that tidal force is causing them to be slightly egg-shaped at the point that they're facing each other. And that sort of like tidal distortion, we would say, causes this sort of modulation of brightness as they spin around.
Great, thank you. The next one, Leslie Sage from Nature for James. Have you looked at the Hipparcos archive for HS Hydra data?
Yeah, Hipparcos was actually one of the data sets used in the discovery by Zasha and Pashka, and we went back and used that in our analysis as well. The successor to Hipparcos, Gaia, I think will also be really useful, but that time domain data won't be available for another couple years. So we'll be dialed into that soon.
Great, thanks. The next one, again, Leslie Sage from Nature, but for Ethan this time. What is the false negative rate?
Yeah, so there's not a simple answer to that. The false negative rate is, eclipsing binaries that exist in the data that we're not finding, is I believe the question. And that depends on 4 different properties of what's going on. The period of the binary, so the more eclipses there are, the more likely we are to find it. How deep the eclipses are. Again, deeper is better, but also just where the star is, because the test pixels are very, very large and lots of stars end up blended together. So you could have 2 nearby stars that basically lie on top of each other in TESS pixels. We don't have the luxury of the very pretty Hubble Space Telescope images. And so each star basically, the nearby stars can sit right next to each other and interfere with each other's light curves that we're measuring. And so that can reduce the amplitude. And so there's not a simple answer. I will say that if the eclipsing binary produces an eclipse depth of about 1% in the light curve, regardless of all these other factors, we can find it. We're nearly complete to eclipses that are at least 1% deep. But if a particular star produces that 1% depth depends on where it is on the sky and how close its other neighbors are, and a bunch of other complicated factors.
Great, thank you. The next one is from Brian Wyatt from the California Academy of Sciences. Question for Ethan. You mentioned false positives. Any sense of false negatives? How many binaries might you be missing? You just kind of answered this question.
That was basically the same question, but yeah, how many we might be missing? We don't have, I can't say we found 300,000 and we have X missing or something. That is something we have been funded to do, though. So we recently did receive funding to extend this and do a full-on test of this, where we inject fake binaries and go in and measure exactly how many we are likely to be missing. So that is a future paper that will be coming out in a year or 2 as we extend this. But this first paper is just meant to be a catalog of what we have found and not what we're missing just yet.
Great, thanks. The next one is for Sagiv. Were the companions always main sequence, or did you consider any evolved companions or even white dwarf companions? And that one's from Pamela Gay from Daily Space on Now Media 21 in Houston.
Yes, thank you for the question. So the companion is a main sequence star, mainly because the jets we inject is in the escape velocity of a main sequence star. If we would take a white dwarf, the velocity will be much higher. So we simulate a particular velocity for escape velocity for a main sequence star, and that is why our companion is a main sequence star.
Great. Thank you. So the next one, again, is from Jan Hatterbach, freelance, for Sagiv again. I didn't get why the companion ends up in a close, stable orbit. Why don't the two stars merge?
Yes, that's another good question. So in usual numerical simulation, I would say that it's partly because numerical issues. So you have some point particles that cannot be actually emerge in the simulation itself because they have some softening radius when you can take the gravitational potential to be too much high, so it will get so there are some numerical problems, and also we have numerical implication because we launched the jets in the center radius, so that's another reason for that. On top of that, at some point the gravitational drag process is actually diminished because there is not enough mass to interact. The companion does that, and the gravitational drag is practically became zero, and the sparring stops. So there's all the combination of these factors. Thanks.
Okay, great, thank you. From Yvette Sendez, freelance for Dan. Why was supernova 1996 CR not discovered until years later? Was it obscured by dust, or was no one just looking or noticing?
Well, the environment that it exploded in is actually quite complicated, and there's substantial evidence for a lot of circumstellar material around it. So at some level, it could have been obscured, and also the reddening in the direction of the supernova is actually quite high. But yes, in fact, it could also be that people were not looking the way that they're looking today. So.
Great, thank you. Leslie Sage from Nature asks Daniel, have you looked for light echoes from the supernova?
We have not, but I don't think that if we were to look for them, we would see anything. The supernova is at 4 megaparsecs away. So at 20 years, the light echo would probably overlap with the supernova spectra itself. So good question.
Great, thank you. Leslie Sage from Nature again for John. Can you determine the type of supernova? Obviously core collapse with a neutron star, but there are many subtypes.
Yeah, good question. We didn't really look into that with our study. Previous studies were able to find, for a while it was a type 1b, and then in 2018 people found some hydrogen, which now there's questions of if it's a type 2b. So definitely core collapse, but unsure of the type.
Interesting. The next one from Leslie Sage from Nature for James. Can you determine if the orbit will ever go into the chaotic regime?
We can't tell yet. The precision on the orbital period from the historical data isn't as precise. If we had tests 100 years ago, I think we could tell, but we didn't. So not yet, but it's certainly possible for these kinds of systems as the third body continues to torque on the binary. They can collapse and end up merging, and you can get the two stars merging into like a blue straggler type object. So it's definitely possible, but whether or not it'll happen within the lifetime of these stars will depend on knowing more about that third body.
Great, thanks. So that's all the questions we have right now. Is there anything in the Slack?
Nothing for our speakers, nope.
Great. Well, we do have time for one more question, or two, if there's a quick one. Rick?
Yes, thank you. Thank you. James and I had a little email conversation going on in the background. So I just want to point out for the benefit of anybody who writes up his results on his star, that the constellation that the star is in is called Hydra, but the genitive form of the constellation is Hydri. It's spelled AE at the end, and the proper way to designate the star would be HS Hydri, if you spell it out. So the constellation is Hydra, Hydra. but if you write out the full name when you use the HS, you should say Hydrae, Hydrae, to get it right.
My Greek is not so good.
Yeah, and the first time when I pointed out the error, the first time I actually made a different error. There's two constellations, the water snake, a male water snake and a female water snake, and they have different names. Hydra is the female, Hydrus is the male, and the genitives are Hydrae, AE, and Hydrae with an I. So they sound the same, but they're spelled differently. But you know me, I'm a former editor of Sky and Telescope, and these things matter to people like me.
Great. Thanks for clarifying, Rick. Goodness knows that I can hardly keep Scorpio and Scorpius straight.
That's a little weirder because Scorpio is astrology and Scorpius is astronomy. So you really want to be careful there.
Well, we are coming up on time, unless
I have one more quickie, a quickie for Ethan. It's obviously phenomenal to find so many more of any particular type of object, but I'm wondering if you could just mention for a moment, you know, what do you think will be the scientific benefit of having found all these? What are the likely things we can learn about stars, stellar evolution, stellar masses, whatever, from this huge new collection of eclipsing binaries?
So I would say off the top of my head, the two big ones are we get to study in a complete sense. Basically, we get a census for how many binaries are out there in all stellar environments, which means all stellar ages. And we can study things about how binary formation or disruption is likely to happen as a function of, you know, being born in a dense stellar environment or being a young system. Are there more binaries that get disrupted as stars age, as they move through the galaxy, things like that. The other thing is we can, with such a large sample, we can measure eccentricities of these systems. And with that, you can get at how stars, again, tidally evolve and might circularize, which is also important for things like planets, is getting at what the tidal parameters are of these stars. That affects all types of objects that are in close orbit around binary stars, which includes planets, which includes stars, and just gets us a fuller sense of how stars might circularize and clear up some aspects of the literature that have been open for a long time.
Thank you. And with that, I'm in the central time zone, so it's 4:30 here. But first off, I'd like to thank all our speakers for some really great talks. I also like to thank our audience, both on this call and on YouTube. And thank you, audience, for all your questions. I'd like to thank the public information officers who helped with the press releases and briefing prep. Our next briefing, which is the second last one of the meeting, will be tomorrow, which is January 15th at 12:15 p.m. Eastern Standard Time. And the topic for that one will be the modern Milky Way. So we hope to see you there. Thank you.